All right, ladies and gentlemen, we are effectively through halfway through chapter 5. So we're going to introduce some triangle relationships, specifically with right triangles. As you know, a right triangle has a 90-degree angle, and there are some very special relationships between side lengths of right triangles that we're going to take a look at today. All right, so the question that we're looking at is, what is the relationship among the sides? So, for example, 3 square tents at the school carnival are situated as shown below. Here's the diagram right here, the green, the yellow, and the blue. The backs, I'm sorry, it's orange, my mistake. The backs of the orange tent and the green tent form a right angle. So you can see that right here. In fact, let me get my drawing tool and give you a, whoops, wrong button, give you a better visual picture of that. The back of the blue tent finishes the triangle. So let me, as soon as this thing is going to cooperate, there we go. Let's use the line. So you can kind of see that it says the orange and the green form the right angle. There that is. And then the blue finishes up the triangle. So I don't know if you want to draw that, trace that with your pencil so that you can see it a little bit better. So that, visually you have the example, and then obviously here is the right angle right there. So there's my right triangle. Investigation. Using grid paper can help to investigate the relationship between the sides of a right triangle. In fact, a lot of times what we do is use different things about the triangle with the grid paper. We can find perimeter, we can find area, we can find a variety of different things, and that's going to be helpful. So, in each figure below, the sides of the 3 squares form a right triangle, just like they do here in the carnival example, and they have labeled the colors so that it kind of looks the same over here. So we've got orange, going with orange, blue and green, and then you can see that there's a little triangle in there, there's a little triangle right here, and there is a little triangle right here. Based on the side lengths of the squares, we can make certain conclusions about the triangles. So that's what we're looking at. It says the sides of the 3 squares form a right triangle. So we're dealing with 3 different triangles right now. Find the area of each square. Okay, find the area of each square. So we're going to kind of leave our picture here. And with grid squares, it's kind of easy in terms of like being able to count grid squares. So they give this to you for the first triangle. Say it says triangle 1, triangle 1's right here. Area of the green square is 1 square unit, because it's 1 square, right? That's pretty self-explanatory. The area of the blue square is also 1 square, because I see 1 square right there. This one, it might be a little bit more difficult to see visually. The area of the yellow square is 2. Well, how is that possible? Well, let's take a look at it. Here's a triangle and there's a triangle. If I take those 2 triangles and put them together, I might have to rework it a little bit, move it around, but that would combine to make 1 square, and then these 2 triangles would also combine to make 1 square. So basically what I have is 4 halves coming together to make 2 wholes, if that makes sense. Okay. So what you are going to do then is fill in the information for triangle 2 and triangle 3. Green, blue, and oh, now it's yellow. Okay, great. So we went from orange to yellow. That's not confusing at all. At least we know what green and blue is, so good enough. At any rate, area of the green square for triangle 2. So again, the green square is right there. That would appear to be 1 square. No argument there. Area of the blue square. Well, let's count. 1, 2, 3, 4. 4 blue squares is what I see. So that means the area is 4 square units. The yellow, apparently, or orange, whatever you want to call it, looks like 1. This and this. Now here's where it gets a little bit tricky. So basically, I don't know if you can visualize this or not. If you take this little piece of this triangle and cut it out and attached it here, you would have this square right there. If that's confusing for you, perhaps this would make a little bit more sense if I erase this real quick and show you. Remember, if you're finding the area of a triangle, area of a triangle is base times height divided by 2, or 1/2 base times height. So in other words, let me use a different color here. If I'm talking about that triangle, okay, so one of the sides is 1 2. You see that? And then this side is 1, right? So 2 times 1 is 2, divided by 2 is 1, which means the area of this big triangle is 1 square unit. So I've got 1 triangle, 2 triangles, 3 triangles, 4 triangles. So, and then the square in the middle makes 5. Hopefully that makes sense. If not, ask me about it. Okay? But basically, the square area is 1, 2, 3, 4, 5 for the yellow square. Yellow. And we're going to move on to triangle 3. Same idea. 1, 2, 3, 4 for the blue. 1, 2, 3, 4 for the green. And this one's going to be a little bit easier to see in the middle. 1, 2, 3, 4. Okay. 4.5, 5. 5.5, 6. 6.5, 7. 7.5, 8. So the big yellow square is 8 square units. Alright, so make sure you have that table filled in. Stop and review if you need to review anything. Okay, hopefully that's not terribly confusing. And we're going to go ahead and move on and answer this question. What relationship exists among the areas of the 3 squares bordering each triangle? Okay, so I don't know if you can see this or not, but like, let's look at this table here. So I think we'll all agree that the yellow square, okay, is the biggest of the 3 squares in each situation. You see that? The yellow square is the biggest. The blue and the green are the 2 smaller, or at least, yeah, they're the 2 smaller of the 3. Look at the pattern of the table here. Okay, so 1, 1, 2, 1, 4, 5, 4, 4, 8. Correct me if I'm wrong, but isn't 1 plus 1 equal to 2? Isn't 1 plus 4 equal to 5? Isn't 4 plus 4 equal to 8? That's pretty wild, huh? So when I'm talking about the relationship that exists among the areas of the 3 squares, what are you going to say? You're going to say something about the sum because they're being added together. That's addition, right? And then here's the sum over here. So why don't we say something like this? The sum of the areas, right? We're talking about the areas. Let me move this out of the way. Sum of the areas of the 2 small squares is equal to the area of the third, isn't it? Blue plus green equals yellow. Blue plus green equals yellow. Blue plus green equals yellow, right? In each situation. So the sum of the areas of the 2 small squares is equal to the area of the third. That's going to help us come to a conclusion about the relationship between side lengths. Okay, so again, pause if you need to, rewind if you need to. Otherwise, we are going to, excuse me, move on, turn the page. By the way, this is page 409. You should now be moving on to page 410. Okay? Work with a partner. Guess who your partner is? If you didn't guess me, you're wrong. Draw a right triangle different than those of the investigation on grid paper. Find the area of each square that is attached to the triangle. Okay, so here's kind of, this is going to be a little bit challenging, but we'll do our best. I'm not going to use a pen because it's going to be a little difficult. So here's what I would do. Just think about the triangles I used on the other page. We had a 1 by 1 by 2, 1 by 4 by 5, and a 4 by 4 by 8. So you can use literally any combination except for those. I'm just going to use a couple that I know for sure there is a certain relationship with. So here's what I'm going to do. You can start anywhere on the grid. It doesn't really matter. And I am going to make, let's go into like right here. And I'm going to go 1, 2, 3, 4 that way. And I'm going to go 1, 2, 3, 4, 5, 6 this way. ooh, you know what? That's not going to work because it's going to be too big. So hang on a second. Let's just erase that. Or just make it a little bit smaller. I had to keep in mind that I'm going to be making squares. So this is not going to work. It's going to be too big. Let's knock this down to 4. What did I have over here? 4. Alright, so let's go to 3. 4, 3 so far. Alright, so 4 and 3. And then just connect those two with a third one, like that, to make a right triangle. Oh, here's the other thing. Doggone it. Sorry, guys. So I'm going to have to move this a little bit more to the middle of the page because what's going to happen is I need to make sure I have enough room to make my square. So there's my 3 side. There's my 4 side. Here's my connector. Like that. That looks a little better. Okay, so here's the deal. This was 4, right? 1, 2, 3, 4. So I'm just going to finish this off by drawing the square around it because I need to find the area of the squares, don't I? So I'm going to go this way 4, and that way 4, and that way 4, right? This over here is 3, isn't it? So 1, 2, 3. 1, 2, 3. 1, 2, 3. Alright, here's what gets a little bit tricky. There's a half, right? And another, and another, and this is going to be off the page. Sorry. It's just the way that it goes today, I guess. You get the idea. So that's going to look like that. Apologize for it being off the grid. Sometimes you got to think outside the box. Ha ha ha. So here's what you got then, right? You've got this is a 4 by 4 square. How much is that? 16, right? You can count all the boxes if you want to, but basically it's a 4 by 4 square. So the area of this is 16. If you want to call that square 1 is 16. Okay. This was a 3 by 3, correct? 1, 2, 3, 1, 2, 3. So 3 times 3 is 9. This, you can't, well, it's really difficult to tell. Based on what we did on the previous page, though, the area of the third square should be the sum of the first two. So 16 plus 9 is 25, which I would be willing to wager that it is true. Again, my lines are not perfect here, but let's try our best to kind of count squares. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then I have the makings of like basically, you know, like 15 and a half, 16. That would be 17, 18 would be in there, 19, 20, 21, 22, 23, 24, 25. It's going to be 25. Just take my word for it. Okay, this is not a perfect drawing. So, fact of the matter though is that it will be 25. All right. Let's try different over here. Let's do something like, gosh, I don't know. Maybe you want to make one up. You don't have to copy what I do. Just make sure you have enough room on either side. So let's do maybe a 2 this way and a 3 this way. 2 and a 3. So I'm going to have a 3 and a 3 and a 2 over here like that. There's my squares. I'm going to connect this to make it a right triangle, which means it's going to go like that and like this. Like that, kind of, sort of. Again, not perfection, but you get the idea. So again, it's easier if I calculate the areas of these. So this is 1, 2, 3, 4, obviously, 2 by 2. So we'll call this square 1 for all intents and purposes. It really makes no difference which is which. 1, 2, 3 by 3 is going to be 9, right? So how much is 4 plus 9? 13. Let's see how we did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's close. Again, my lines are not perfect, so trust me when I tell you 4 plus 9 is going to equal 13. Okay. So what's the point of all this? The point of it is to see if I take the squares away, there's going to be a certain relationship between these numbers. Okay, 16 plus 9 equals 25. 4 plus 9 equals 3. So that's kind of the idea. Let's analyze then. On the grid paper shown right here, draw a right triangle so the two shorter sides are 3 units and 4 units long. Okay, we kind of did that already up in the previous example, but we'll do it again just for giggles. So I've got anywhere, it doesn't matter. 3 by 4. Let's do the 4 this way. 1, 2, 3, 4. We did this already. 1, 2, 3 this way. Okay? Does that make sense right now? On the grid paper shown, draw a right triangle so the two shorter sides are 3 units and 4 units. Draw squares attached to each side of the triangle. Alright, so basically it's the same thing that we just did up at the top. We're going to connect just the leg sides though. So I'm going to do my 3 over here. Right? And oops, I don't have enough room. So I'm just going to extend this past. Again, think outside the box sometimes, right? So what we're looking at then is this is 3 by 3, which is going to be 9. This one is 4 by 4, which is going to be 16, right? So I know what the other one is going to look like. What is the area of each square? Okay, so I got basically 16 square units, 9 square units, and then the big guy is going to be 25 square units. How do I know that? Because that's the exact same thing that I did up here. Okay. What is the length of each side? All right, well, think about it. This side is 4, correct? This side right here, this leg of this triangle is 4. This side length is 3. And this is, again, where it gets a little bit tricky and it's kind of hard to see. What do you know about the relationship of these numbers? Like how is 4 related to 16? Well, it's 4 times 4, isn't it? How is 3 related to 9? Well, it's 3 times 3, isn't it? So if this is 25, if the area of this square that was happening over here is 25, what could you say about the side lengths? It's probably going to be 5, don't you think? So, because 3 times 3 equals 9, 4 times 4 equals 16, and 5 times 5 equals 25, yeah? Does that make sense? Isn't that kind of what we did over here also? So that's the relationship that they're trying to show you. What is the length of the longest side of a right triangle if the lengths of the two shorter sides are 6 and 8? Okay, well, what is the length of the longest side of the two shorter sides? So now we're talking side lengths of triangles. How much is 6 times 6? Boom, you got it. How much is 8 times 8? Boom, you got it. Why did I do that? Because we were adding squares. If this is the length of the side times itself would equal the area of the square, right? Okay, let's check this out. How much is this? 100. Why is that significant? Well, what number times itself equals 100? Exactly. 10 centimeters. So I can expect the third side, the longest side, to be 10 centimeters long if the first side is 6 and the second side is 8. It would be a 6, 8, and 10. Okay? So, again, pause anywhere you have to, rewind. You know the drill. What is the relationship then among the sides of the triangle? Okay, this one's a little bit more abstract. So here's the side lengths, right? 3, 4, 5. This is this side length, 6, 8, and 10. What is the relationship? Well, let's think about something like square roots, because the square root of 16 is 4, right? 4 times 4 is 16. The square root of 9 is 3. 3 times 3 equals 9. The square root of 25 is 5, right? 5 times 5 equals 25. Over here, the square root of 36 is 6, the square root of 64 is 8, and the square root of 100 is 10. That happens to be the relationship of the sides of a right triangle. In fact, we're going to go ahead and say with certainty that the sum of the squares of the two smaller sides is equal to the square of the longest or largest. It really doesn't matter. That's the relationship. Square the sides. 4 squared is 16, 3 squared is 9, 5 squared is 25. The sum of the squares of the two smaller sides, 16 plus 9, is equal to the square of the longest side, 25. You see it? The sum of the squares of the two smaller sides, 6 squared is 36, 8 squared is 64, is equal to the square of the longest side. 36 plus 64 equals 100. That was 10 squared. So that is the relationship that we're talking about. And that is going to lead us into our lesson on the Pythagorean theorem. So here's your responsibility. I'm assuming you did this with me. So you're going to go ahead and tear out 409, 410. Make sure that your name is on it and turn it in to the mailbox. And I believe the next direction is going to be to go into Elluminate, find any missing work that you have, and work on that and get it turned in as well. Thanks for your attention. I hope this made sense to you, and it'll make it nice and easy when we get back from the weekend to go right into the Pythagorean theorem. Okay, guys? Have a great day.